You are listening to the PFAS Research and Remediation podcast series produced and created by Arcadis, with funding from the Environmental Security Technology Certification Program, ESTCP grant number ER 23-7692, through the United States Department of Defense. All opinions, interpretations, and conclusions expressed belong to the hosts and guests and do not represent the views or policies of the Department of Defense. In our second season, we interview a broad panel of experts who have each contributed to the growing knowledge base around remediating this emerging chemical of concern. Well, Charles, thank you so much for joining us today. You've been doing contaminant remediation and characterization for quite a while now, and in recent years, you've started looking at PFAS. Would you mind talking about how you got into PFAS and what were some of the first things you started looking at? What were some of the early problems?
Yeah, it's a great question. So I think I dove into PFAS world probably about 13, 14 years ago when there were some statements of need from the Air Force to look at remediation of PFAS. And what's kind of funny about this is, I saw that statement of need. I'd never had done anything with PFAS. And then I decided to look at electrochemical treatment. Well, I had never done anything with electrochemical. So electrochemical treatment of PFAS. And it got funded. So lucky me. It was an exciting project because it was all new. But that really kicked me off. I've worked with Chris Higgins at School of Mines with that, and it's not too many people better than him to work with. So that was that started many things.
Yeah. So you're not afraid of novelty and big adventure.
Not afraid of novelty. No. That's what makes it fun, right? Yeah. That's why a lot of us are in this.
You've been looking at leaching in the Vados zone from these traditional fire training areas. And let's talk about some of the specifics of your current project. What are some of the primary objectives and what are the different aspects of PFAS transport are you looking at?
We have a couple of projects ongoing where we're looking at PFAS desorption and leaching through the unsaturated zone in these AFFF source areas and potentially their migration to underlying groundwater. This is really a pretty important problem because what the actual leaching is can really drive potentially what some of the cleanup goals are for the DoD at their sites. And there's really a lack of a lot of fundamental understanding of these processes. And even where we think we have a fundamental understanding, it really hasn't been observed or validated at the field scale. And as you know, what understanding we have in a batch system or a simple bench scale experiments, sometimes that gets pretty blown up when you go to the field. So kind of really trying to connect the dots between the understanding we've gotten as a research community here at the bench scale and really trying to show what's happening in the field. So that means, going out to multiple sites. And, there's really two types of approaches that at least I try to think about for these types of questions. One is that really deep dive, real intensive evaluation at a single site. And that's really informative because you have tons of data and all these parameters you evaluate, but it's only one site. So as how typical or atypical is that site? The other typical approach in these projects is to do maybe a much more scaled back evaluation, but do it at multiple sites and try to see what you can learn going from one type of soil or one type of climate or one type of PFAS mix to another. So that's what we're trying to do kind of in a very broad sense at these sites. One of the tools we're using at these sites is our porous cup suction lysimeters, and they've gotten a lot of attention in PFAS world over the last 5-6 years now. But it's important to remember this tool has been around for decades. And there was a lot of study and evaluation of these really by the agricultural community and looking at things like pesticides, looking at things like nitrates. So it's been kind of fun to dig back into some of that literature, not have to repeat some of the same errors and mistakes that were maybe done early on. But using this as a tool to extract and measure the actual pore water and measure PFAS concentrations in the unsaturated zone and trying to understand, what is a relationship between what you measure in a collected soil sample and what's actually in the pore water, and then how quickly is that pore water moving to groundwater. So we've done a lot of things like that in trying to understand the PFAS phase behavior in these real systems.
So you're generating empirical data and you're, I assume, trying to match that against conceptual or maybe quantitative models about PFAS transport.
Yeah, so we're trying to basically generate the real data set and then apply some of these phase equilibrium models that have been developed and maybe validated in some cases at the bench scale and really see if they hold true at the field scale. There's a couple of mechanisms in particular that we've taken a close look at. So I talked about the surfactant behavior of PFAS, and that means they can accumulate at air-water interfaces. And there's been a lot of good studies by a lot of great researchers showing how that impacts transport and phase behavior, but again, at the bench scale and pretty controlled systems. So one of our objectives have been to go out in the field and say, hey, does this really seem to be important in the field with all the complexities and heterogeneity and unknowns that are there? And I think, what we can say with some level of confidence, at least for the handful of sites we've been out to, is that, this is real. We are seeing some real impacts of this.
So to be clear, you're saying significant retention at air-water interfaces.
Yes.
In the vadose.
Yeah. So when you look at the phase distribution and look at the migration, I think we can say that, there's definitely a substantial amount of mass at the air-water interface. And when we see collapse of those air-water interfaces during things like rainfall events or other things that might cause, say, the water table to increase, we see PFAS concentrations increase in the pore water, right? So that's a pretty solid line of evidence that this air-water interfacial accumulation is important and does seem to be impacting mass discharge to underlying groundwater.
Yeah. Let's talk about absorption in this source area. So high concentration AFFF release. What about classic chemisorption?
Absorption or uptake to the soils in general is really important. So, the air-water interfacial accumulation that we mentioned, we've seen that that's important. It's new, it's exciting, and definitely requires study. But you still go back to a lot of these source areas to the more classic, how much is stuck to the soil and how quickly or how readily does that desorb into the migrating pore water next to it. And what we're finding is, yes, air-water interfacial accumulation is important. But for a lot of these sites, at least to understand the long-term, over decades, leaching behavior, I really think some of the data suggests that it's really more driven by this soil-water partitioning than maybe the air-water interfaces. One of the things we've looked at in particular, both at the bench scale, but then seeing how it plays out in the field, is just what is the nature of PFAS desorption from the soil, because that's really what has to happen for leaching to occur. And we've been looking at both the kinetics of that as well as some of the equilibrium or pseudo-equilibrium behavior. And what we're finding for a lot of sites is that PFAS release from the soil is in fact rate limited. There's some fraction that might come off readily, but there's a fraction that seems to come off very slowly. And I mean on the order of weeks to months in some cases. And that can have a huge impact ultimately on what the mass discharge to underlying groundwater is. And it might also have a big impact on what's really an appropriate soil cleanup standard too. If there's some fraction of PFAS that is coming off extremely slowly, and at some point extremely slowly becomes not really environmentally relevant, that can be really important. And it kind of points to the difficulty of assigning a generic soil cleanup standard without knowing what's really available and without understanding how much can come off. And there, in fact, might be a fraction that is at least effectively irreversible. And I think trying to understand or know what the mechanism for that is important for multiple reasons, right? One is just an additional line of evidence when we're trying to show that to various stakeholders or regulators to kind of give another level of assurance that this is real and not just some poor measurements or not the right conceptual model. And I think it's also important to understand, if there's ways we're trying to either enhance that or maybe in some ways mitigate that so we can get it off for some sort of treatment purpose. So, these mechanisms, again, can be just slow micropore type diffusion. It could be this kind of rubbery or glassy organic matter state, which can lead to a retention of PFAS, or it could be some other mechanism we haven't fully understood yet.
So it sounds like we have some hypothetical mechanisms that are promising, but we still don't really understand what drives this apparent rate limited desorption. How about precursors and precursor transformation?
Yeah, well, that's, what you measure in terms of the perfluoroalkyl acids. In a lot of sites may only be a small fraction of what's there, whether in the actual soil phase or even in the pore water. We're also getting some insight into what's happening there. One finding that I thought was really interesting is one of the sites we looked at. We were doing some bench scale batch desorption tests. We knew we had a lot of potential precursors present, especially PFHXA precursors. Then when we did the batch experiment, our mass balance told us that we produced a lot more PFHXA in the aqueous phase than what we initially had in the soil. And that could only really be explained by precursor transformation, right? So we saw that, we thought it was neat, but as we were doing some of these flushing tests in the field, we also saw that we flushed through the shallow unsaturated zone more PFHXA mass than we knew what was present there. So we saw this again, the same thing happen in the bench scale that what we saw in the field. And this has been a site where it's been 25 years plus since its last exposure to AFFF, but yet we're still seeing some slow precursor transformation occur. Now, maybe some of the water flushing we did through here helped to stimulate that a little bit for one reason or another, but there's still biotransforming precursors in this shallow vadose zone that are contributing, at least in part, to the overall PFAS mass discharge to underlying groundwater.
Yeah. So the vadose zone is a pretty complicated place, spatially variable in saturation and temporally as well. And also redox can change over time and space as well. So certainly complicated. Does it get easier and simpler in the saturated zone?
Yeah, certainly in terms of phase behavior in the saturated zone, you don't have the big changes in water saturation. The air-water interface isn't a big player. I think you have, in some respects, a lot less complexity there. I think trying to tackle fate and transport in the saturated zone is, in general, going to be easier than in the unsaturated zone. So I think tackling the unsaturated zone first, where at least we see some of the highest mass and some of the highest concentrations, is probably appropriate. But I don't always think understanding what's going on in the unsaturated zone is always going to give us the full story or necessarily even point us in the right direction. You need to look at the site more holistically and understand, hey, even if I were to treat this perfectly, what benefit is this going to give me? Right. Now, at this particular site, we're still trying to figure out, well, what is sustaining these high concentrations in shallow groundwater? It could be kind of the classic back diffusion from some low permeable zones that are present at this site. It also may be tied into some complexities at or near the water table. Some funny things can happen there, and there's a lot of water table moving up and down. Maybe that's part of the problem. Maybe there's something else going on there geochemically that's causing that. It's great we're putting all this investment in the unsaturated zone, and I think we need it, but we can't neglect what's going on in some other areas, and we need to really understand what's sustaining these plumes.
Yeah. So for the research community, what do you think are the highest near and mesotherm priorities with regard to understanding transport fate?
Yeah, that's a great question. And if you sat down and asked 10 different people, you'd probably get 10 different answers. So I'm sure my answer is going to be biased to what I look at and maybe what I like. I still think some of the key questions come down to just some of the classic questions we've had for these contaminants. And for PFAS, it's, I think, still understanding the phase behavior. Are they forming some of these larger structures when they absorb onto soil? And how important is that? I really think the soil desorption kinetics issue and understanding that is ultimately something that's controlling the long-term leaching and also how plumes are being sustained at a lot of these sites.
Right. Well, Charles, this has been a great conversation. Is there any other aspects of your research that you'd like to hit on before we close?
No, I mean, I think I've probably covered the stuff that was probably most on my mind and heart to talk about. But I think before big decisions are made on what we need to treat and what doesn't need to be treated, I think it's important to really understand what is treatment going to get you.
Yep.
And some of that just means to be patient and understand fate and transport. Certainly we need to protect receptors now and do things like that, and that's certainly important. But I think to get the most value out of treatment, we need to understand fate and transport. And I think our history has showed that with previous classes of compounds. I think that's going to be the same with PFAS.
Yeah, those are great thoughts. Well, thanks again for your time. It's been a pleasure.
My pleasure. Thanks.
Thank you so much for listening. This podcast was funded by ESTCP and produced by Arcadis. The interview was conducted by Craig Devine, and our guest today was Dr. Charles Schaefer. If you're interested in more information on Charles's work, please visit SERDP-ESTCP.org and search for Charles Schaefer. If you've conducted your own research on PFAS and are interested in sharing your work, please email Teresa Gillette at teresa.gillette@arcadis.com. That's THERESA dot GUILLETTE at ARCADIS.com. And please consider following the podcast through SoundCloud to stay up to date on new episodes.